Question number 19. The question is question number 19. A tungsten wire 0.5 mm in diameter is just stretched between two fixed points at a temperature of 40 degrees Celsius. Determine the tension in the wire when the temperature falls to 20 degrees Celsius. It is given within bracket. Coefficient of linear expansion of tungsten is equal to 4.5 into 10 power minus 6 per degree Celsius. Young's modulus of tungsten is 3.45 into 10 power 10 Newton per meter square. Yeah. So let us note down once what is given and what you are asked to find was just a tungsten wire 0.4 mm in diameter. Diameter is equal to 0.5 mm. So usually diameter is one, but usually in this kind of case we may need a radius. We have to take the radius. We will take later. But in SI units we can write it as 0.5 into 10 to the power minus 3 meters. Right? 0.5 10 power minus 3 meters. It is just stretched between two fixed points. Means like this, two fixed points. So it is stretched between two fixed points like this. This is a wire. This is just stretched between two fixed points. The temperature of 40 degrees Celsius means initial temperature of 40 degrees Celsius. Temperature we are representing with theta 1. Okay, why? Because we are supposed to deal with the tension. So tension we take it as T. So temperature will take it as theta 1. Temperature theta 1 is equal to 40 degrees Celsius. Determine the tension in the wire. Determine the tension in the wire. T is tension. T is tension. Okay, theta is temperature. Temperature is theta. Determine tension in the wire when temperature falls to 20 degrees Celsius means theta 2 is equal to 20 degrees Celsius. Given that coefficient of linear expansion of tungsten, the coefficient of linear expansion in symbol is alpha. Alpha of tungsten. Tungsten is equal to 4.5 into 10 to the power minus 6 per degree Celsius. Okay. Next modulus of tungsten is Young's modulus of tungsten is equal to 3.45 into 10 to the power 10 Newton per meter square, right? So these are the given data and we are asked to find what is the tension, how to find tension. You have to understand is if initially if this is a wire, tungsten wire kept between two rigid supports at temperature theta 1 is equal to 40 degrees Celsius, it will have some okay, it will have some tension, and when the temperature decreases, of course the tension may decrease, but you are asked to determine the tension in the wire when the temperature falls to this. So not at 40 degrees Celsius, when temperature decreases, what is the tension in the wire you are supposed to find? That means that is nothing but change in tension, or you can take it as when theta 2 is equal to 20 degrees Celsius. Tension here, it may act like this. What is the change in tension you have to understand? Okay, change in tension. So you know Young's modulus Y is equal to F L by A into delta L. Here F is nothing but the force which is producing the stress. When a force F acts on an area, it produces a tension, what you call stress, that in turn gives the strain delta L by L. So here this force can be taken as tensional force. Okay, so you can take this as T into L by A into delta L. Okay, but here this further you can also write it as this L by bringing here you can write it as T by A numerator by delta L. You bring this here, you can write it as A by L. Why? Because we know that why we are writing like this way is we'll understand this. We are asked to find tension, right? So for that purpose I can take it as otherwise directly here T is equal to this way I can write. Let's take this implies you can take tension T is equal to y a delta L by L, by L. So here directly can take delta L by L is a strain, linear strain. This delta L by L can be taken as where delta L by L in terms of temperature change. The change in length due to temperature difference is nothing but alpha into delta theta. where alpha is temperature coefficient of this material. Here it is tungsten, and delta theta is change in temperature. So this gives delta L by L. Is it clear? So if you substitute this, we can write it as tension T is equal to Y of tungsten, Young's modulus of tungsten, into area of tungsten, into delta L by L is alpha into delta theta. Got it? Yes. So here, y is given, alpha is given, theta 1, theta 2 is given. Here you can find out the delta theta, change in temperature, and what is area. Here diameter is given. From this we have to write down as area is equal to pi r square, area of the wire, area of cross section of the wire. As it is having a diameter, means it is supposed to be having some radius, or means it is supposed to have cylindrical structure. So you can take it as pi r square. So here, but radius is given, not given, diameter is given. So you can write it as pi into radius can be expressed as diameter by 2 whole square. Okay, so this if you substitute here, you get the T is equal to y a into, oh sorry, a you can take this one, a you can take this as pi into d by 2 whole square into alpha into delta theta. Okay, now all are known parameters. Y is given, d is given, alpha is given, delta theta is given. If you substitute and simplify, we'll get it is approximately 0.6097 Newton. Will get tension, approximately 0.6097 Newton will get. Okay, and substitute and simplify this. So that's it. Anything? Try to revise all once again. Seventeen. So, two wires of the same material, same two wires of same material have masses in the ratio of 3:4. The ratio of their extensions under the same load if their lengths are in the ratio of resistance. Ratio of their extensions. Okay. Number 17. So it is given that two wires of the same material have masses in the ratio 3:4. Masses in the ratio 3:4 means, let us take is m1 by m2 is equal to 3 by 4. Right? Two wires having same material means you have to understand that y1 by y2 is equal to 1 by 1 or 1. Hmm? Having same material and having masses in the ratio 3:4, the ratio of their extensions, the extensions can be taken as delta L or E, or so delta L1 by delta L2. Ratio of their extensions under the same load can be nothing taken as force. So F1 by F2 is same, means they are equal to 1 under the same load if their lengths are in the ratio, if their lengths L1 by L2 are in the ratio 9 by 10 is what are the extensions, ratio of extensions, the same load acts, and provided if the lengths are in this ratio, what is the ratio of their extensions. We know that. Hmm? We know that Young's modulus y is equal to f L by a into delta L. We want delta L. So from this, delta L is equal to f L by a into y, right? A into why? But it is given that two wires are made of same material, and this is the extension. So we are asked about ratio of extensions produced in two wires. Delta, you can say delta L1 by delta L2 is what provided. Two wires are made of same material, means this is constant. Y is constant, right? And they're having a same applying same load, right? F is constant, and the ratio of lengths are given as this. Provided masses are in this ratio, they have given a masses ratio. But how to express the masses? You have to, area is not given, masses is given. Means we have to think that how to express this area in terms of mass. We have to think. Is to understand that, let us multiply both numerator and denominator with L by L. L by L. Why? Because to express mass, we need volume. If you know volume, then volume can be expressed as density into density equal to mass by volume. So volume is equal to mass by density. You can write mass by density. So how can you express area in terms of mass? So after converting into volume, then you can take, because it is mentioned that so what do you call the hmm, lengths are different, but materials are same, both are made of same material and the same load is acting. Under these conditions, you have to think in such a way that maybe volumes are same, having the same. Usually volume will be same, whatever be the length. Under extension, volume remains same. Under that condition, you can try to express the volume in terms of mass. For that purpose, try to convert into volume, then to mass.
So we are taking
Yes, volume. So it's not like length is varying, we are taking volume, because mass is given. So that means area is not given. So to express area in terms of mass, you have to convert into volume, then volume into mass. So I have to take it as L square by volume. Then L square by the volume can be taken as density. As density is equal to mass by volume, we can take volume is equal to mass by density. For this purpose, we are taking into volume to express in terms of mass. So this is mass by density. Density of both materials are same, means density will be same, right? So further, you can write it as this implies delta L is proportional to L square by m. Delta L is proportional to. So from this, you can also write delta L1 by this is what you are supposed to find out. Delta L1 by delta L2 is equal to L1 by L2 whole square into this is M1 by M2 or M2 by M1, M2 by M1. That's it, right? Is equal to L1 by L2 is given as 9 by 10. So 9 by 10 square means into 9 by 10 into M2 by M1. M2 by M1 is what? M2 by M1 is 3 by 4. 3 by 3 by 4 only. M2 by M1 or M1 by M2? M1 by M2 is 3 by 4. So M2 by M1 is 4 by 3. I have to take it carefully. This 4 by 3. So 3 is cancelled. So we'll get 9 3 is 27, 27 fours. Or 4 is 12, 12 nines. Just find out what is this. Or you can also cancel out 2 twos, 2 fives. Again 2 ones, 2 fives. So 5 into 5, 25 is 27. So 27 by 25. So you get delta L1 by delta L2 is equal to 27 by 25. 27 is to 25. Got it? So option, which option is right?
fourth option.
That's it.
So if length is varying and the area is not given, means you have to go with volume.
Yes. That means what you have to understand is that volume remains constant. That's what you have to understand. One second, did I share this? Okay. So next, question number 6. Right. The question is, a wire can be broken by 400 kg weight. The load the load required to break the wire of double the thickness wire and the load required to break the wire of double the thickness of the same material will be in kg weight.
So kg means mg or kilograms.
Kg weight is conversion relation from the kg weight to Newton is uh, g times g newtons. It's 9.8 newtons. Kg, you have to take it as mg. So that g extra will should come out. So you have to take it as a wire can be broken by 400 kg weight. The wire can be broken by load of F. It can be taken as 400 kg weight. In the newtons, it will be 4
Those.
400 or 1000. 400 kg weight. It is equal to 400 into, let us take the g, this in the conversion relation between kg weight to Newton is 1 kg weight is equal to 9.8 Newton or approximately 10 Newton. Depending on the requirement, you can take like this any value. For simplified calculations, you can take 10 to 10 Newton, so 4000 Newton you can take. The load required, this is a load, the wire can be broken by this much. This is called as braking force. That implies braking force. Braking force is equal to BF. Braking force is equal to 4000 Newton. If this is for a braking force, then the load required to break the wire of wire of double the thickness. So this is a breaking stress required to break a wire of having some thickness, some thickness T or X or whatever it is. So if the wire is having double the thickness, then what should be the breaking force required? What should be the breaking force required if the wire is having double the thickness? Wire is having double the thickness of the same material. Same material means Young's modulus will be same. Y1 will be equal to Y2. Okay. This is the first case. What is the breaking force in second case? So that y1 is equal to y2. What is the breaking? This is breaking force in kg weight units only you want. So here this you can write it as, of course, at the end you can convert it to kg weight. No problem. So y1 equal to y2. Like, the thing what you have to,
Please, I
yeah.
want to take
Yes.
elongation.
Like thickness means just is not elongation. Thickness means how thick it is. Like you can take it as that in terms of area. So what you can understand here is, elongation. What you mentioned here to break. Hmm, stress. Breaking force is there means you have to use the word breaking stress, or simply stress is equal to force by area. So if you take this as breaking stress, you can call it as breaking force by area. So breaking force is given, and if it is having some thickness means some particular area, then breaking stress will be having some breaking stress. Breaking force is 1, right? We don't, so that it will have some breaking stress. Now the next condition here is, mm, if the thickness becomes double, what will be the breaking force is the question. What will be the breaking force? The ratio of these two will be, of course, is equal to constant for a given material. So if this changes, this also should change this, so that this will be fixed, constant. In such case, if we take, you can say that the breaking force stress is equal to force by area, or in this case, breaking force, simply you can take it as force is equal to breaking stress into area. Stress will be, you can say, if it is constant, this is proportional to area. Area is nothing but for a cylindrical cross section, it will be pi r square. or breaking force, or simply force is proportional to r pi r is equal to pi r square or proportional to r square. R square. The thickness can be expressed in terms of radius or diameter or whatever it is, right? So, but not in terms of area. The thickness means in terms of diameter, right? Or radius. Diameter is nothing but 2r. 2 is a number. You can take simply f proportional to 2r whole square means r square. So you can take f proportional to r square. So first case breaking force you can take it as f1. Second case f2. So f2 by f2 by f1 is equal to r2 by r1 whole square. Yes. So this implies f2 is equal to r2 is twice the thickness, means to 2r by r. If you take r1 is r whole square into f1, right? It is 2 square is 4. 4 f1. What is f1? 4000. So it is 4 into 4000 is equal to 16,000 Newton. But kg weight form, if you want, 1 Newton is equal to 1 kg weight by 10. So you reduce 1. So it is equal to 1600 kg weight. So you can say F2 will be equal to F2 is equal to 1600 kg weight. So is there any such option? 6 2. Yes, this is the breaking force in such case, right?
Thank
Right. So the question is four identical hollow cylindrical columns of steel support a big structure of mass 50,000 kg. The inner and outer radii of each column are 30 and 40 centimeters respectively. Okay. So the inner and outer radii of each column are 30 and 40 centimeters respectively. Assuming the load distribution to be uniform, calculate the compressional strain of each column. Young's modulus of steel is this. Four identical hollow cylindrical columns. Of steel support a big structure of mass. So let's consider there are hollow cylindrical columns. Hello. చెప్పరా క్లాస్లో ఉండాలి. Here we are. This one, right? Yeah. 8 1, right?
Yes, sir.
So there are four cylindrical columns. Let's see, this is hollow cylindrical column. Means inside nothing will be there, but they're having inner and outer radial. So this is a cylinder with another outer structure is there. So it is having this is the axis. This is having inner radius r1 and outer radius r2. So here some material is occupying here. This is the like this. Actually, this is so solid part is only in this part. Here is it is hollow. Like this, four cylinders are there. One, two, again with this kind of structure, and again one more. So like this, hollow means this is a hollow, and this part is occupied with this part is occupied with the material. This part is occupied with material, right? And here again one more, four, right? Four. So like this again, this is cylindrical pillar. So here this part is occupied with material, but this inside is hollow. That means this part is occupied. This is a material one. The outer, so front one like this. inside refill is there, right? Like outside is the pen is there, like, but that inside space is not empty. The inside the refill is empty, like that. You have to consider. That is called hollow with this kind of structure. So here is four identical hollow cylindrical structure means length is same of all, means height or length, whatever you can say, whatever you can take it as, and inner and outer radii are same for all. These are supporting a heavy load. These are supporting like heavy load. These are supporting heavy load is kept on this. Hmm? These columns all are made of steel, support a big structure of mass 50,000 kg. This mass M is equal to 50,000 kg, right? 50,000 kg. The inner and outer radii of each column are 30 and 40 centimeters respectively. So inner and outer radii are R1 is equal to 30 centimeters and R2 is equal to 40 centimeters respectively. Okay, assuming the load distribution to be uniform, calculate the compressional strain of each column. Young's modulus of steel is 2 into 10 power 11 Pascal. So what else is given? Inner and outer radii are there. Assuming the load distribution is uniform, means the mass is distributed uniformly, so that it is exerting a downward force of equally. Actually, this is, if you say somewhere the center of mass is acting, so total weight is acting downwards as mg. But because they are acting on all, this will undergo compression. Same amount of compression. That means this force will divide it like equal. So I mean not equally, accordingly. So you can say there is some of this force is equal to total force. Like that you have to take, like this is what you have considered like in the simple case, right? If you have two wires connected in series and parallel, this series combination, or if you have two wires connected like this, parallel combinations. If this is connected to a load and this is connected to a load, if a load is connected to F here, total elongation is equal to elongation in this plus elongation in this, delta L1 plus delta L2 equal to delta L. Whereas here delta L is same in both. So that means the F, whatever you are applying here, that will distribute as equally F1 and F2. F1 plus F2 is equal to F. Same way here, this is elongation is taking place here, but here in this case elongation is taking place, but in this case same way, but load is on top, so compression will take place. So same compression will take place on all the rods. So what is happening is what is mentioned here is all are made of, all are identical, right? Hmm. So, but that means force is distributing equally. If this is something like F1 and F2, there are different materials. F1 plus F2 is equal to F, but here all are identical. So you can say total weight is equally distributed. F by 4, F by 4, F by 4, something like that. Okay, then if it is equal to F. So what you can understand from this is, assuming the total load distribution is uniform, calculate the compressional strain. Compressional strain means delta L by L. Strain. Here, compressional strain. In this case, the strain is called elongation strain. Here, compressional strain of each column. The Young's modulus of provided Young's modulus of the steel is 2 into 10 to the power 11 Pascal. So, what you can take? First thing, Young's modulus formula. Y is equal to F L by A into delta L for each rod. From this, as we are asked to find delta L by L, so you can write this L here and bring it here. Then you can write delta L by L is equal to, if you have L here, delta L by L, y is equal to F by A into delta L by L. If you bring it here, F by A by L, get F by AY. You got it? So in this case, F is nothing but what? We are asking, we are trying to find the compressional compression. What compression? Compressional strain, compressional strain on a single wire. On single wire, how much force will act, and hence what is the area, and hence what is Young's modulus. Young's modulus is same for each one. Area will be what? Area here is nothing but area on which mass is distributed is the area, right, of the wire, area of the wire. So it is because it is an inner and outer radii, this you can write it as area is equal to outer. So from here to here, outer radius is r2, outer radius is r2, inner radius is r1. So but in this only mass is distributed, so area of the outer one minus area of the inner one, if you subtract the area of this middle one, you will get. So you have to take this as pi r2 square minus pi r1 square r is equal to pi into r2 square minus r1 square. You have to take that will be the area. Okay, and y is given, and f you have to take accordingly. Then if you substitute the values, you get the compressional strain. Okay, so it is therefore what is compressional strain is single one, right? So we can say F is actually nothing but total mg is the force is mg, right? Here this is area. One thing is clear. Right? If one less is given directly, then what is F? F is equal to the total force is mg, but this force is, you can say, force on one is nothing but mg by 4, mg by 4. So m is this, g you can take 10, okay, as nothing is mentioned here, by 4. So it is 50,000 into 10 by 4. So what is this? Hmm? Two twos, two fives, two 25s. So 25 into 5 is 125. Huh? 125,000 Newton is F1, force on each one. So F1 you have got, and A, this you have substituted values and find out A. A also you can find out here separately. A is equal to pi, substitute the values. Pi into R2 square minus R1 square. R2 is 40, R1 is 30. What is square minus 30 square? 1600 minus 900. How much? 1600 minus 900. 1000 minus 900 is 100, 700. 700. Then, oh, it is okay, centimeter square. If you convert into meter square, you'll get 10 to the power minus 4. Yes. Then it will be 700, right? So 700 means can be expressed as 7 into the power 2. So 7 pi into 10 to the power minus 2 meter square is A. So you got F, A, Y is given. If substitute it here, then here this implies delta L by L, compressional strain. So it is obtained to be with 1, so 2.78 into 10 power minus 6 overall value after substituting this one and this one, everything. Okay, F here and A in the denominator, Y is 10 to the power 11 in denominator. On simplifying everything, you'll get 2.78 into 10 to the power minus 6 is a ratio, no unit. This will be the final answer we get. Okay. Thank you.